Right. Okay, so the first thing you're going to do is you're going to check that you've got the right exam paper. If you're in the exam, you're going to checking that you've got the foundation paper. It will have the date on it. Okay, and you're doing a foundation paper. Now, if you want to open it up, we'll start with question 1. Okay, you've got a diagram there. Okay, it says which element is graphene made from? This is what we call an AO1 question, which means it's dependent absolutely on subject knowledge. It's one of those bits you know or you don't. However, you'll see later on there are clues. So even if you couldn't do this, so this is a low answer. Now, I want you to be going through these simple questions, literally just ticking as we go through. Okay, I won't give you time to do writing for this. So for this one, it's going to be carbon. Okay, so we're just going to tick that box and then turn the page. Okay, question 2, part 2, it says each atom in graphene has one delocalized electron. Okay, it says complete the sentence, choose the answer from the box. So delocalized electrons allow graphene to, now we have act as a lubricant, conduct electricity, be used as a fuel or dissolve in water. It's going to be delocalized, means that it's not going to be sitting, it doesn't stay in the same place. So it's going to be conducting electricity. Okay. They like to give you some quite simple tick box type questions to start off with. Now, it says which structure is a fullerene? Now, you've got a clue on here. It's saying carbon atom. Now, that question 1 was already talking about what element was in there. If you couldn't remember, that will give you the clue for that section, that part 1. It's told you it's carbon. So we've got a carbon atom, we've got oxygen atom and hydrogen, oxide and magnesium, and then a carbon atom again. Now, a fullerene is one of those big structures, and it is going to be with the delocalized electrons. So it's going to be the bottom one. That's our nanotube. Okay, it's not the top one, because these carbons have got 4 bonds on them. Each one of them has got 4 lines coming out of it, which means it's diamond. At the bottom, the carbons have only got 3 lines coming out, which means that it's going to be a nanotube. It's got delocalized electrons. Okay, over the page. Shows part of a large hydrocarbon molecule. Which 2 elements are in hydrocarbons? Well, you've got hydro and carbon, so it's going to be hydrogen and carbon. Part 1.5. Choose an answer from the box. Complete the sentence. A large molecule represented in figure 2 is it an atom? Well, it can't be, because there's too many parts of it. Is it a metal? Well, we know carbon and hydrogen are non-metals. Is it a polymer? It could be. Is it a salt? It could be. But this structure, if you remember, is showing a repeating chain. That's what that little N there means. Means that we've got this repeated again and again. And that's what a polymer is a repeating set of units. So it's going to be our polymer. Okay, at the bottom of the page, choose an answer from a box. Metals can be stretched into wires because the layers of atoms can attract. Well, that's going to stick them together too closely, isn't it? Bond, again, it's tight. It's holding it together tightly. Slide, well, that would be the right sort of idea. And vibrate. So we can work it out. It's going to be between 2. Now, if it's going to be stretching, we're thinking about sliding. So it's going to be slide. Okay, that one. Over the page to question 2. Okay, questions about electrolysis. I know people struggle with electrolysis. So how many different elements are in the formula AgNO3? Well, we've got an Ag, we've got an N, and we've got an O3. So we've got 1, 2, 3 elements. So it's going to be that second box. And then it says how many atoms. Well, I've got 1 Ag, I've got 1 N, and then I've got 1, 2, 3 oxygen. So I've got 1, 2, 3, 4, 5 atoms. Okay. Often it's easier if you literally just draw a line at the top, so you can just count the lines up afterwards. Right. Over the page, electrolysis. It says an electric current is passed through silver nitrate solution, and it shows the apparatus, and it contains these 4 different ions. Where do the H plus and OH minus ions come from? Well, we know that that is a silver nitrate solution. Now, solution means that it's going to be dissolved in water. So the only things in there, in the liquid in the electrolyte, because this is where our ions come from, is from our electrolyte. It's not air, not electrodes, it's going to be the water. It's that bottom box. Okay, when you're ticking boxes, if you are unsure and you think to yourself, I'm going to review the paper and I'm going to come back because I'm not sure, you can do that ticking pencil if you are doing an exam paper. Okay, so you can rub it out. But nice clear tick over the page. So silver ions, so the Ag plus ions and H plus ions are attracted to the negative electrode, which is the cathode. Give a reason why. Well, these two have a positive charge, and it's the negative electrode. So we're going to write in, it's a 1-mark question, the opposites. So opposite charges attract. Okay, so all I'm just saying is I'm recognizing that that's a plus and this is a minus, so they're going to attract together. Okay, question 2. Silver is produced at the negative electrode and not hydrogen. What does this tell you about the reactivity of silver? Again, this is one of our AO1 questions. And AO1 is expecting you to know a specific piece of information. Okay, so silver is less reactive than hydrogen. We've got silver is less reactive than oxygen. Silver is more reactive than nitrate, more reactive than water. Well, it's actually asking you about silver and not hydrogen. And the only one that's mentioned those two is that top box. Okay, so you can take clues from the question. Okay, 2.6. Hydroxide ion is attracted to the positive electrode. The equation shows what happens. Name the gas produced at the positive electrode. So we're looking at a product. So it's going to be one of these. And we're looking for which one's a gas. Now we know that oxygen is a gas. Okay, so we're going to write that one in. Okay, over the page. Right, we're on 2.7. We've got a lot of information there. When you've got a big question, sometimes it's worth actually looking at the question before you read all of that text, because that can waste a lot of time sometimes. Okay, so the question, you're going to find the actual question down right at the bottom. It says name an indicator and give the colour of the indicator in sodium hydroxide solution. So actually, this stuff we don't really need. So especially if you're running short on time, you might want to always look to the question at the bottom and then see what you actually need to find out about in that top section. Okay, so our indicator, now we're going to use universal indicator for this. And we're looking at it, what happens to it in sodium hydroxide. Now a hydroxide is an alkali. So an alkali, with universal indicator, is going to go purple. Yeah, well, you can put blue or purple. both are actually correct. Okay, we've got that OH minus ion going on there for the hydroxide, which is what's going to change the colour. Okay, over the page, and we're on to question 3. This question, a bit later on, I'm going to give you time to complete because it's got a longer answer in there. We have. Right. So, a fluorine ion has 7 electrons on the outer shell. Figure 5 shows part of a dot and cross diagram of hydrogen fluoride. Complete the diagram. You should only show the electrons in the outer shells. So it's got 1 in there, which is what's coming from our hydrogen. Oops, let's move that up so it's clearer. So it says we've got 7 in the outer shell. Now you're going to end up getting 1 mark just for recognizing, because that's a covalent bond, I've got to have a pair of electrons in there. And then I'm going to add the other 6. So I've now got 1, 2, 3, 4, 5, 6, 7 electrons in that outer shell. I'm showing now that I've got that covalent bonding pair in the middle to get my 2 marks. 1 mark for that bonding pair and 1 mark for the fact that I've only put 6 in that outer shell there. Okay, over the page. Question 3.2. What is the state of oxygen difluoride at -200? Okay, so we're going to have to use the information on the previous page. So we're looking for -200. The information I've got is it says -145 and -224. So it's something in the middle there. So if it's boiling at this one, it's turning into a gas. If it's melting at that one, that's a solid. So we must have a liquid in the middle. Yeah? So we are going for a liquid. It's not aqueous. So there were 2 possible ones. It couldn't be a gas because that was past the boiling point. Couldn't be a solid because that's below the boiling point. Aqueous means it's dissolved in a solution, and we haven't got a solution there. We've got 1 substance. Okay, it says. So the next one, what change of state occurs when oxygen difluoride is cooled from -220 degrees to -230 degrees? So we are going, if we look at our diagram, we're going from a liquid to a solid. So it is going to be freezing. We're going from liquid to solid because we are freezing. Now, okay, so now we've got some slightly longer answer questions, and these are the ones that particularly we need to type of practice. Okay, it says potassium reacts with fluorine to produce the ionic compound potassium fluoride. Figure 7 shows the transfer of electrons during the reaction. So we've got electrons moving. Describe what happens when potassium reacts with fluorine to produce potassium fluoride. Write about electron transfer in your answer. Okay, it's using describe. Describe means you need to be looking at that diagram and telling me how it has changed between what it was at the beginning and what it is now. Okay, so the first thing that I can see is that potassium has lost an electron. It had an electron there, it's now got nothing, but it now has a positive charge. So the first thing I'd put in would be the fact that potassium's lost an electron and has now gained a positive charge. The second change that we can see is that fluorine has now gained an electron. You've got that extra one there, and has a negative charge. Okay, so the fluorine has gained an electron and now has a negative charge. Now it's 5 marks. They literally are able to get those 5 marks. Okay, can you write down your answer? So we're going to talk about the fact that potassium loses electron and gains a positive charge, and that the fluorine gains electron and gains a negative charge. So it's going to form a positive ion, and the fluorine is going to form a negative ion. So that first statement would have got me probably 3 out of 5 marks. By adding, forming a positive ion and forming a negative ion, I've gained my 5 marks. Okay, do you need time to write that down?
What's the word after?
You can put this in your own words. Oh, I'm trying to get this so it's... Is that easier? Can you see? Okay, let's move. Are we okay? Can I move on? Next question. We're still on question 3, but part 5. Again, this is a 4-mark question, so it's going to ask. It's asking me for some information. So, potassium fluoride is an ionic compound. Explain why ionic compounds have high melting points. Use the following words in your answer. So, attraction, energy, and ions. Okay. So, first of all, I would start that off by saying, but just you can write these in bullet points, but I personally find it easier to write it in a sort of a sentence. So I would start that with ionic compounds have a high melting point because that's the questions it's asked me. Explain why ionic compounds have a high melting point. So ionic compounds have a high melting point because... Now, if we're talking about attraction, if it's got a high melting point, then there must be a strong attraction. So I'm going to work my way through this list of words. Yes, because there is a strong attraction. What's the attraction between? It's going to be between our ions because they are oppositely charged. We've actually answered that in the previous question, didn't we? We looked at the fact that they've got different charges. But I also need to incorporate this idea of energy. So it will take a lot of energy to break them. Ooh, let's do an M, not a W. So ionic compounds have a high melting point because there is a strong attraction between ions, because they are oppositely charged. So it will take a lot of energy to break them. Okay? The only thing I could have added into that is why they form this, and it's because they form a giant ionic lattice structure. Okay, that's the only other part. So I reckon you could easily have got, just by using those 3 keywords, you've got your 3 out of 4 marks. The only thing they haven't talked about is the ionic structure, that lattice structure. Oops, keep moving this, don't I? The ionic lattice structure, and that's that extra little bit of knowledge that's going to get you your 4th mark. They have a giant lattice structure. Okay, but that was a 13-mark question in total, that mark question 3, and I reckon you could have got most of them. Okay, question 4, and we're already halfway through the paper now, and these are still on the lower level questions, so we haven't gone up to the higher tier, not, you know, the crossover questions. Those standard questions are on the low tier. So it says the questions about compounds of oxygen. The reaction between carbon and oxygen is exothermic. What does exothermic mean? Like every scientific word, we can generally work it out from its word root. Exo meaning outside, or to give out, thermic heat. Okay, so it's going to give out, or it's going to give out heat energy or transfer heat energy to its surroundings. Okay, so pop that one in. Okay, at the bottom half of this page, then we've got 4.2, and it's giving you 3 diagrams. It says, which is the correct reaction profile energy level diagram for an exothermic reaction? Now, this is the level of energy. If it's giving energy out, it means our products are going to have to be lower in energy than our reactants were to start off with. So it's going to be that top one. If we look at the bottom one, we started with a low amount of energy and it got hot. So if we look at the second one, low amount of energy and it's had to increase. So that's pushing something up a hill, which means it's going to take energy. That's going to be our endothermic. And the bottom one of the diagrams, there's no change in the energy. Okay, so it's the top box. Over the page. Okay. The percentage by mass of oxygen in carbon dioxide is calculated by the equation percentage by mass, number of atoms of oxygen, times relative atomic mass of oxygen, times 100, divided by the relative molecular mass of carbon dioxide. Okay, where do we go with that? It's a maths questions. Maths questions are your friend. Even if you couldn't remember anything about any of the previous stuff about exo and endothermic, bit of maths is easy. Okay, so calculate the percentage by mass of oxygen in carbon dioxide. So all you're essentially going to do is plug some numbers into the equation here. You've been given the equation. Always show your workings when you're doing a maths, when you're doing any maths on these papers. So it says number of atoms of oxygen. Okay, so how many atoms of oxygen have I got in CO2? So CO2, yep, so I've got 2 oxygens. So I'm going to have a 16, so I've got 2, yep, times, and it says relative atomic mass of oxygen, so 2 times 16 times 100, and then divided by the relative molecular mass of carbon dioxide. Okay, so what is the relative molecular mass of carbon dioxide? We need to work that out. So we've got a carbon, which is 12, plus oxygen, which is 16, plus oxygen, which is 16. If you wrote that down, you have got 2 out of 3 marks. Well, you've got to plug the numbers in, you get 1 mark. Second one, but you've also shown me that you've been able to do these calculations here, so that's you've got 2 marks anyway. Even if you forgot a calculator in the exam, you'll get a lot of the marks just by showing that you know how to do the sum. Okay, so essentially we've got 32 over 44 times 100, which is going to give us 72.7%. Okay, now it's going to give us actually 72.7272727272, but we're going to round that to 1 decimal place. Okay, 72.7%. Are we okay with that one? Over the page. Balancing a chemical equation. Right, there are several ways of doing this. Easier and more difficult ones. The way I would go about this is, okay, how many have I got? I've got 2 hydrogens here and I've got 2 hydrogens here, because this is my reactants on this side and these are my products. We have to make sure we've got the same number of each type of atom on both sides. So I've got 2 hydrogens and 2 hydrogens, that's fine. I've got 2 oxygens here, but I've got 3 oxygens here. Okay, now the only thing I need to make that into an even number. I can only do multiples of 2, can't I? So if I say, okay, well, I'm going to put 2 lots of that. Let's try 2. You can always do these in pencil. So I've got 2 lots of this molecule plus O2. So what does that do to my numbers? So I've now got 2 hydrogen here, and now I've got 2 lots of 2 hydrogen here, which is 4. Okay, so I've now got 4 hydrogen on this side, but I've only got 2 hydrogen on this side, so I'm going to need to put double that molecule. So I've now got 2 of that molecule. Let me check the numbers again. So I've got 2 lots of 2, which is now 4 hydrogen, 2 lots of 2, which is 4 oxygen. I've got 2 lots of 2 hydrogen, 4 hydrogen, 2 lots of 2, which is 2 oxygen plus 2 oxygen, which is 4 oxygen. So I've now got that balanced. Okay. Okay, now again, another maths question. There are several ways of tackling this one. This is the way that I would do it. It says, so 6.8 grams of hydrogen peroxide decomposes to produce 3.6 grams of water. Calculate the mass of oxygen produced when 68 grams of hydrogen peroxide decomposes. Okay. Now, it's asking me for oxygen, isn't it? So in my equation, I started off with 6.8 grams of hydrogen peroxide, and I made 3.6 grams of water and some oxygen. I can fill in that some oxygen box because the sum of this has got to be 6.8. So my first bit of maths is going to be 6.8 minus 3.6 equals, yeah, which will give us 3.2 grams. The next part of the question, so that's my first mark, it's just doing that simple sum, recognizing the sum of the products is the same mass of as the reactants. The next part of my work, the answer is going to say, if I start with 68 grams, what is the relationship? So instead of 6.8, I've got 68. So I'm going to do 3.2 times 10 because the relationship between 68 and 6.8 is times 10. So I'm going to have 32 grams of water. Because remember, the mass of our reactants, mass of our products. Balanced. Okay, are we following? Okay, periodic table time, question 5. This is where we get to the more difficult questions. Okay, so the first half of this paper has all been on low demand questions. These are the questions that you would find on the higher tier as well. So these are our questions that are giving us level 4s and 5s. Okay, first one's quite an easy one. It says, compare Mendeleev. So we're looking about atoms and chemical elements. Mendeleev's periodic table has groups of elements with similar properties. Figure 8 shows part of his periodic table. So it's showing me, this is his version. This is an old-fashioned version, not a current version. It says, compare Mendeleev's periodic table with the modern periodic table. Which group is missing from Mendeleev's periodic table? If I look at the modern periodic table, on here I've got group 1, 2, 3, 4, 5, 6, 7, and then I've got nothing there. Whereas on here I've got 1, 2, all the way across group 0, haven't I? So the one I've got missing is group 0. Okay. Over the page. In the early periodic tables, some elements were placed in the wrong gaps. Mendeleev overcame these problems. In the wrong groups. My apologies. Mendeleev overcame some of these problems in his periodic table. Give 2 ways that he did. Okay. First of all, if you notice here, he's left a space. So that first mark is literally he's left gaps or left spaces for the missing elements. Okay. And then secondly, if we look, we've got different order in masses. Okay, so he's changed the different order based on their masses. Oops. Okay, so change the order based on their weights, their masses. Okay, at the bottom of that page then. Now, can we please be using rulers, and if you are unsure, use a pencil for this. So it says, draw one line from each scientist to the discovery the scientist made. So we've got Niels Bohr. So discovered electrons orbit the nucleus, existence of neutrons, mass of atom concentrated in the center, and protons found in the nucleus. So Niels Bohr was one of the later ones. He worked after Rutherford, so they knew about a nucleus then. So it's where the electrons are orbiting. So make sure it's a straight line, it's drawn with a ruler, and it goes to both boxes. Don't do a vague line that's sort of ish somewhere in the middle because it looks nice. Make sure it touches both boxes. Secondly, Chadwick is our existence of neutrons. Okay, so Chadwick discovered the existence of neutrons. Okay, over the page. So a beam of electrons, neutrons. So this is and protons can be separated by passing them through an electric field because they've got charge. Figure 9 shows the direction of 3 particles after entering the electric field. So we've got our beam of particles going through the middle. Now it says charged particles are attracted to the oppositely charged plate in the electric field. We know this. So if we've got a particle that is bending that way, it must have a negative charge, mustn't it? That must be a negatively charged particle. If we've got one that goes straight through and is unaffected, it must have no charge on it. And if we've got one that goes through and is bent towards the negative, it must have a positive charge. So it says which direction, A, B or C, does each particle follow? So we know what the charges are on these particles with their directions. We've just got to match them up with our electrons, neutrons and protons. Now we know our electrons have a negative charge, so the one that I've put a negative next to is A. We know our neutrons have a 0 charge, and the one that went straight ahead was B. And then finally our protons has to be C. They've got a positive charge. A, B, C. The chances of that coming up in that order again on an exam, I wouldn't think it's high, but you never know. Okay, calculate the mass of 1 atom of sodium using the equation. This is not physics. We do not need to remember equations. This has been given to you. So the mass of 1 sodium atom equals the relative atomic mass divided by Avogadro's constant. It tells you that Avogadro's constant is 6.02 times 10 to the 23. Give your answers to 2 significant figures. So you're just going to put those numbers, again, we're going to write the equation out, substituting the numbers, and then you're going to use your calculator. You do need to know how your calculator works, and you need to understand standard form. So the sum that we would do would be 23 divided by 6.02 times 10 to the 23. Okay, just to write that on your exam paper, you have 1 mark. To plug it into your equation and then come out with 3.8 times 10 to the minus 23 is going to give us 3 marks. If you do 3.8 and a considerably longer string of numbers from your calculator, that will only get you 2 marks. But if you can get it to 2 significant figures, so 3.8 times 10 to the minus 23, that gets you all 3 marks. So write it into the final box at the bottom, 3.8 times 10 to the minus 23. Okay. Again, maths is our friend when it comes to this. What are you doing? Okay, 5.6. The radius of a sodium atom is 227 picometers, and it says a picometer is 10 to the minus 12. The radius of a nucleus is 1/10,000th of that atom. So 1/10,000th of an atom is its nucleus. Which calculation shows the radius of a sodium atom's nucleus? Okay, so we're going to need to have a look through these and discount some information. So this is 227, that number's in there, yes, times 10,000 meters. That's not going to work, is it? Because that's massive. We're talking a huge amount. We're talking in meters, yeah. So it can't be that one. This one's better because we've got the 227 and we've got this radius of the nucleus, but it's not taken into account anything about the fact it's picometers. It's just given 227. Okay. Then we've got 220, so it can't be that one. 227 times 10 to the minus 12. Well, we like that bit, but we've got a problem with this. It's not the 1 over 10,000 that was in the question. So in the end, it's going to be our final one. So 227 times 10 to the minus 12. So that's taken account of that. It's taken account of that. And then finally, it's taken account of that. So it's a bottom box. Okay. This bit's representing the atom, and this bit is representing the nucleus. Over the page, question 6. Right. Actually, some students investigated the change of temperature as sodium hydroxide solution is added to sulfuric acid. There's lots of information. It's giving me a method. I'm not going to bother reading that for the moment. I'm going to go and look at the question and see what that tells me. So the volume of sodium hydroxide solution is a variable. Which 2 words can be used to describe this type of variable? Tick 2 boxes. So we've got volume of sodium hydroxide. Okay, let's go back to that method and see what the volume of sodium hydroxide is being used. So some students investigated a change in temperature as sodium hydroxide solution is added to sulfuric acid. This is the method they used. Put 25 cm cubed of sulfuric acid into a polystyrene cup, measure the initial temperature, add 4 centimeters cubed of sodium hydroxide, oh, well, that's got sodium hydroxide in it, to the dilute sulfuric acid, stir the mixture, measure the higher temperature, repeat 3 to 5, so until 40 centimeter cubed of sodium hydroxide is added. Okay, so I'm adding it bit by bit and then I'm measuring something else. So if I'm adding it bit by bit, I'm choosing how much I add. It means it's going to have to be my independent variable. It's the thing that I'm choosing to change. So out of those bottom 3, it's got to be the independent variable. Now the top 2, categoric and continuous. Categoric means different types of things. Continuous means a bit at a time. Means that the numbers are touch, as it were. So categoric would be something like bananas versus apples versus peaches for your lunch, whereas continuous is time or temperature. Now we're measuring something that's on a continuous scale, isn't it? So that's it's continuous and it is independent. Okay, over the page. Right, dilute sulfuric acid has an initial temperature of 24 degrees centigrade. You notice first thing I did was circle that. They're telling me for a reason. Figure 11 shows the highest temperature. Calculate the change in temperature. So I'm going to need to read off this. I need to first of all work out what my scale is. So if I've got 30 and 35 there, 31, 32, 33, 34, 35. So each one of those must mean 1. So my reading on here is coming back. So my reading on here, okay, is going to be 31.5. So change in temperature. So I'm looking for the difference between those 2 numbers. So 31.5 minus 24 is going to give me 7.5 degrees temperature change. Okay. When you're doing something like that, it looks very, very simple. Double check that you've understood what the scale is, and that's representing 1 each time and not 2. Okay, this is showing the student results, which means we're probably going to have to do something with graphs. It says determine the volume of sodium hydroxide solution that gives the highest temperature change. Okay, use figure 12 to help you. So I want the highest temperature change. So back on my graph, which is the one, these are our temperatures. So I'm going to go for the one that's got the highest. Okay, and I'm going to trace that back down onto my x-axis, and that's going to come up at 26. So the volume is going to be 26 centimeters cubed. Okay, it's simply reading a graph. Remember, even if you're unsure of any of the other questions, always a graph question you can do. It's just reading information. Okay, in figure 12, the temperature when 16 centimeters sodium hydroxide is added is anomalous. Do we know what anomalous means? It means that it doesn't fit the pattern. So suggest one error that could have been made in the method which would cause this anomalous result. Oh, I don't need to look at the graph for that one. So why do you think we could have got an anomaly? Because on here we've seen that the temperature hasn't gone up quite as high as it could have. Okay. There you could have several things. It's a 1 mark question, but there are probably several answers that you could put in there. You could say you didn't stir it, or you didn't wait for the highest temperature to arrive to be recorded. Okay. So if you fill in that one, please. If I was really floundering with that question, look back at the method that was given on that first page, and you can usually find a clue in there as to what could have gone wrong. So if you look in these two bits here, stir the mixture and measure the highest temperature. That's going to be our sources of error. Okay. Question 6.5. We've got a 3 mark question, but again, it's maths, and maths is our friend. Sodium hydroxide solution in this investigation contains 80 grams per dm cubed. Okay, so we've got a number 80 and we've got dm cubed. The student uses 40 centimeter cubed of sodium hydroxide solution. Calculate the mass of sodium hydroxide in 40 centimeter cubed. Okay, now we've got 80 grams per dm cubed. Now a dm cubed is a litre, which is a 10 by 10 by 10. That's what a litre is. It's 10 centimetres. We call it dm cubed because it's 10 centimetres by 10 centimetres by 10 centimetres. So a 10 by 10 by 10, which is 1,000. So I've got 80 centimetres cubed. It's 80 grams dissolved in 1 litre. So that's a way of representing. So 80 divided by 1,000 tells me I've got 80 grams of solvent, of solute dissolved in my dm cubed, my 1 litre. Because by writing it as 1,000, I've converted. Instead of a dm cubed now, I'm talking centimetre cubed. I've got the same units. We need to be really, really careful. Same units, cm cubed and dm cubed. So I've changed that dm into a cm cubed. Okay, so that's cm cubed. All right then. So 80 divided by 1,000. So I've got that's showing my relationship, my fraction of solid in solution. And then it says calculate the mass of sodium hydroxide in 40 centimeters cubed. So if I multiply that by 40, that's going to give me the amount. That's going to give me my answer. So I've said that this is the amount of solute in my solvent, and multiplied by 40, which is the amount I need. Okay, which will give me 3.2 grams. 3 marks available. 1 mark is available for that bit, for understanding that a dm cubed needs to be turned into a cm cubed. 1 mark is for writing this out and realizing that we multiply by 40. 1 mark for actually writing 3.2 on the answer line. Okay, over the page. Question 7. It says, this question is about metals and metal compounds. Copper oxide reacts with hydrochloric acid to produce copper chloride and water. Copper oxide is insoluble in water. Copper oxide is gradually added to hydrochloric acid until excess. Sketch a graph. You need to go to your next lesson. We've nearly finished now. Sketch a graph on figure 13 to show how the pH of hydrochloric acid would change. Okay, so it wants me to work out how the pH is going to alter and draw it on this set of axes. Okay, now I need to work, I've got to suss out what the information is in the question. So copper oxide and hydrochloric acid. Okay, the copper oxide is added to the hydrochloric acid until it's in excess. So we start with an acid. If we're going to start with an acid, it means we're going to start right down here. Okay, so I'm going to start my line either at 0, but certainly at some point under 3. It's a strong acid. I'm going to need to start my line there. Okay, but how high does it go? Now it says copper oxide is insoluble in water, which means it's not an alkali. It means it's a base. And it's gradually added until in excess. Now, it's a base, so it neutralizes an acid. But if it's in excess, it means it's going to neutralize all of the acid available. So there will be no more acid in there. However, it says it's insoluble in water, so it's not an alkali. If it's insoluble, it means it can't go above pH 7. So our line is going to go up to pH 7, and then it's going to go flat at pH 7. So the increase is as we're adding the copper oxide, and then it goes flat at 7. Now, if we were doing sodium hydroxide, it would just keep going up to 14. But we're not. We're adding we're adding a base, so it will only go up to 7. Okay, over the page. This is our 6-mark question. There will be 1 on every paper, and it will always be towards the end of the paper. Again, it's easy to find at least 4 out of those 6 marks. We should be getting at least half of them. So it says, magnesium reacts with hydrochloric acid to produce magnesium chloride and hydrogen. Plan an investigation to find the accurate volume of hydrogen produced from magnesium. You do not need to write about safety precautions. Okay, so I don't have to worry about safety specs. But I am going to need to talk about hydrochloric acid produce and reacting with magnesium. This is one of the required practicals that you have already done. So the first thing you would do, or the first thing I would do, probably is draw a diagram. There's a lot of space here. Drawing a diagram of equipment, I can often get a lot of the marks already without having to write anything. So I would draw a diagram. So I'm going to have a flask. I'm going to have a flask, sidearm flask, that's going to go. Now I need some way of it says on here how to accurate volume of hydrogen peroxide produced. So I need to measure the volume of gas. Now I could do that several ways. I could do that with a measuring cylinder in a water bath, so displacement like that, or I could use a gas syringe. Now the most accurate, and it says accurate, so I'm going to choose a gas syringe. So my gas syringe, it doesn't matter how beautiful your drawing is, because you are going to label it. Okay. And we've got a bung in here. We've got some acid, and we've got magnesium. I'm going to add labels to this. So I've got a gas syringe. At the moment, you don't need to be drawing anything. You can watch. I'll model what I'll do for the answer, and then you can write your own answer in a minute. So I'm labeling. I've got bung. I've got a conical flask. And the way I can get extra marks just from this diagram, not just drawing it, is when I label it, I can put volume. So instead of saying hydrochloric acid, I could say, okay, 25 centimeters cubed. I've specified the amount of hydrochloric acid I'm going to put in. There, I've got magnesium ribbon. What I could do is write 1 centimeter of magnesium ribbon. By specifying the quantities, I've actually provided, if somebody wanted to repeat my experiment and reproduce my results, they could. The only thing that they would need to know is the concentration. So I could have 1 molar hydrochloric acid. That's my concentration. Now, what we can do now is actually bullet pointer method. But that's essentially all the information that we're going to need to put into our method. So first of all, I'm going to need to measure my, I'm going to set up the equipment. So set up flask and gas syringe. 2, I need to measure both of my reactants, don't I? So I could either measure 1 centimeter of magnesium ribbon. You could also weigh it, by the way. You could also weigh 1 centimeter of magnesium in order to be even more accurate. 2, step 3. Now, can you see I'm writing as bullet points? There's no point in me writing this in prose. I'm going to measure 25 cubed of hydrochloric acid. Now I'm cheating. I'm going to put HCl down there, which is a symbol for hydrochloric acid. And now I'm going to go 1 molar. 1m means 1 molar. It means I've shown how concentrated that acid is. Okay, and pour into flask 4. I'm now going to add magnesium ribbon and quickly replace bung to ensure no gas is lost. Okay. So I've set it up, I've got the practical going. What am I measuring? Now it says accurate volume of hydrogen produced. So I'm now going to record the volume of hydrogen once all the magnesium has reacted, and then to ensure that I am getting those 5 and 6 marks, I'm going to repeat experiment in identical conditions to check results. Okay, or for check for reliability. Right, if you'd like to get that written up, you do not need to write what I've written exactly. You can't see it all for a start, but you need to have included those points. But just by drawing the diagram, you would probably get 3 or 4 marks. Probably 3 marks.
Let's give it another.
Is anybody still writing? Okay. Right. If we're all done, let's go to the last questions. And that's it. That's a whole exam paper done. Here we go. So again, maths is your friend. Graphs are your favourite questions. Because it doesn't matter whether you can remember anything about the content, you can work with a graph. So it says calculate the gradient or slope of the line on figure 14. So we need to work out what the gradient of that line is. Okay. Now, how do we calculate a gradient? We do y over x. Yeah, so whatever the value, because it's gone from 0, whatever the value on y is, so y divided by the value on x, we substitute the numbers in. Okay, so where does it come to? Now I can draw this. So I can use my ruler and my pencil. So I know it's 6. So I know the x value is 6. Okay, so I can write that bit down. So I know the x value is 6. I just need to double check where it is on the y-axis. So use my ruler to trace it across. And it's going to be... Now, the scale is obviously... Because there's 1, 2, 3, 4, 5 between the 2 units. It means it's going to be 0.2 for each of them. So 0.2, 4, 6, 0.8. So it's going to be on 4.8. There we go. 4.8 divided by 6. 2 mark question. That's one of them. If I actually get the answer right and write down 0.8 in the answer line, that gives me that second mark. But again, if you didn't have a calculator, you could still write that and you still get one of the 2 marks. Over the page. Now, and this is why so these questions have got harder as we've gone through it. It says determine the mass of copper that can be produced from 75 grams of copper oxide. Okay, let's go back to that graph. Now we've got 75 grams of copper oxide. What does the graph show us? Now, it's not going to give us 75 grams, but it can give us 7.5 grams, and we can work with that. So if I want, so that could be 7 point. So that's 7. Yeah. So 7.5 is going to be in there. So I'm going to need to extend the line. So what they need to see is that you have used a ruler and matched it up and extended the line. Okay. Okay. Now I need to work out where 7.5 is. So I need to work out where 7 is for a start. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 10 units between the 6 and the 8. So we're doing it obviously 0.2 for each of these squares. So 1, 2, 3, 4, 5. So that's giving me 7 here. And I'm going to go halfway between. If it's 7.5, I'm going to go halfway between. And I'm going to get my ruler and I'm going to draw up to that line that I've already extended. Okay. I've done it wrong. Gosh. I know. I've done it wrong. What mistake have I made? I've looked at here and it's of 7 point. It's 75 grams of copper oxide, not 7. That's the Oh yeah. Oh no, it is right. That's all right. I did do it right. Okay. So I've traced that up there. That is right. And then I'm going to trace it across to that y-axis. Here we go. Doubting myself here. Okay. Which is 6. Okay. So I've extended the line up. I've worked out where 7.5 is on that x-axis. I've mapped it across to the y-axis, which has given us 6. So it says, determine the mass of the copper oxide. So I've used, so if I've got, 7.5 times 10 is going to give us 75 grams. Yeah. Or the vice versa. So instead of 6 is going to give us 60 grams. Okay, so the answer is 60 grams. So we get our 3 marks, not for what's written in here. We're getting our 3 marks, one of them for 60, one of them for showing I can extend the line up, one of them for drawing, and remember to draw on your axes. Okay, this is your exam paper. No, Michael, sit down, please.